Hello, everyone. In this video, we're going to look at example 4 in section 6.4. So this example is very similar to example 3. So I really encourage you at this point to pause the video and work out this example for yourself, and then watch through, maybe even skip ahead to see how your solution compares with the one that we give here. All right. So after you've had a chance to do that, let's look at this problem together. Okay, so in this situation, we're given a rectangular aquarium having a length of 3 meters, a width of 1 meter, and a height of 2 meters. And we're told that it's filled to the top with water. Given that the water has a density of 1,000 kilograms per meter cubed, find the work required to pump all of the water over the top edge of the tank. All right, so in this problem, they're even telling us how to see the dimensions on this tank. And similar to the last problem, we're going to assume that at any slice or level of the aquarium, that this slice of water is going to move just straight up and over the tank top. Okay, so at this point, we should know the drill, know the method of how to complete a problem like this. We need to chop up our water into slices and compute the work needed to move one slice to the top of the tank. So I'm going to go ahead and just draw in that slice to help us visualize what's going on here. Okay. So here's our slice. Give it a little bit of thickness here. Okay. So again, our goal is to compute the work needed to move a slice to the top. And as we saw, work is equal to force times distance. And force is a weight. Don't want to use W again, but force we compute as the weight, which is the mass times acceleration due to gravity. Okay, so let's first focus then on that weight of a slice. Weight of slice. Okay, so as we saw in the previous example, we're going to compute the weight of a slice by calculating the volume, because we're dealing with a three-dimensional object here. The slice is a three-dimensional, so it has volume, times the density, times that acceleration due to gravity, or the force by gravity. All right, so let's go ahead and work this out. And actually, before we do that, let's just go ahead and check units. So volume is going to be a meter cubed, because we're given meters for our dimensions here. Density is a kilogram per meter cubed. So those meters cubed cancel out, and we're going to get kilograms for that mass, which is an appropriate mass unit. And then multiplying by acceleration due to gravity, which is meters per second squared. So then we're going to get joules. Nope, not joules yet. We'll get newtons. Okay, so the units check out. So let's go ahead and compute those values then. So volume of a slice, or a slice looks like a little rectangular prism here. So we can compute the surface area of a slice and of the top of the slice, and then multiply by the thickness of the slice. So here, that top piece will be 2 times 1 times 3. Oh, actually, I don't want to actually quite do that. Let's think about that a little more carefully. So the top of the slice has a dimension of 2 by 3. I was computing the volume of the entire aquarium, which is not the volume of a slice. So for us, that would be 2 times 3 times the thickness of our slice. So the thickness of our slice is a little change in y. We'll call it y. We could call this variable anything we want. We could call it L, like for length. We could call it A for like aquarium. We could call it X. I'll call it y, so times dy. And we can check. We get meters cubed here. Meters, meters, meters. Okay, so there's the volume. And then we're given the density as 1,000 kilograms per meter cubed. So it's going to be multiplied by 1,000. And then that'll be multiplied by that 9.8. And we already checked units, so we can go ahead and multiply those numbers together. Before you do that, I hope you caught my mistake here. This 2 meters is referring to the height of our tank, right? We're told that the 2 meters high. So I misread our picture here. I was going just a little too fast. So what we should have here is 3 is the appropriate measure for this, but this 1 refers to the distance or the width of our tank. So how does that change? Not too bad. It actually simplifies things a little bit. Instead of this 2, we should have a 1. Okay, nice job for those of you who caught that. All right, so let's go ahead and use our calculator to multiply these numbers together. And when we do that, we get 29,000, and feel free to check me on this, 29,400 times dy, and that will be newtons. Again, since we already checked those units. So that's a weight of a slice. So then to compute the work of a slice, we just need to multiply the weight by the distance that slice travels. All right, so let's write that out. Distance slice travels. And we already decided that we're using y for our variable there. So we're going to let y represent the length or distance that the slice at y travels. So it'll be y meters. So then now to put the work together, so work to move a slice will be that 29,400 dy newtons times y meters. I'm going to write units down with those calculations, just so I can be clear that my units are coming out correct. So Newton meters, which will turn out to be joules. Okay. Awesome job. So we just computed the work required to move a slice. So now we can just put that together to compute total work. Total work. So for that, we're going to compute the integral. We're going to add up the work needed to move each of these slices that we're making. So 29,400 y dy. All right, so the final step here in setting up this integral is to determine our range of y's that we're going to use. So we can think of, well, what's the smallest y we're going to have? Well, this tank is filled with water. So the slice occurring at 0 meters down will not have to go anywhere. So then the smallest y can be at 0. And then the longest y will be, or the longest distance traveled by a slice will be the slice at the bottom of the tank. And it will have to travel this 2 meters. So the largest y is going to be is 2 meters. So we can put that on our integral. So our integral will go from 0 to 2. And let's go ahead and compute this integral. We're getting pretty good at computing integrals like this now. So what we get when we compute that antiderivative is 29,400 times y squared over 2, evaluated at 0 and 2. So we can plug in 2 here. So 29,400 times 2 squared, which we can just compute as 4 over 2, minus, and then when we square 0, we're just going to get 0. So I'll leave it at 0. Now, when we put that in our calculator, we get something around 58,800 joules. So in the end, the total work needed to move all of the water out of the top of the tank is 58,800 joules. Awesome. Great work going through this example.